Hello and welcome to our video providing an overview of our DAFx paper, which is entitled Parametric Spatial Audio Effects based on the multi-directional decomposition of ambisonic sound scenes. I'll begin with a high-level overview so that you can get a general idea of what this work is about. We are interested in taking ambisonic sound scenes, which can be derived from microphone array recordings, or they can be created synthetically. And we want to extract spatial parameters over time and frequency that describe what is going on in the sound scene. We then want to use these spatial parameters to divide the sound field into its individual spatial components, which then allows us to manipulate these spatial components individually so that we may create some interesting spatial audio effects. And finally, we then want to reproduce this modified spatial sound scene over the intended playback setup. Which can be headphones, an array of loudspeakers, or we can simply re-encode the manipulated components back into the Ambisonics format. So I will now rewind a little bit to provide some background information. Here is a slide depicting the traditional Ambisonics framework. The idea is that based on a purely linear and time-invariant operation, the microphone array signals or monosignals can be encoded into these intermediate ambisonic signals, which follow the directivity patterns of spherical harmonics. These intermediate signals can then be decoded to headphones or loudspeakers rather flexibly. The decoder never needs to know which microphone array was used, since these operations are decoupled. And the decoder doesn't need to know what kind of scenario the ambisonic signals are describing, since we're talking about purely linear operations at the moment. There are then a number of spatial audio effects or sound field manipulations that may be applied onto these intermediate signals. Sound field rotations are perhaps the most common in order to accommodate head tracking, but there are also other operations such as sound field mirroring, warping, or directional loudness modifications. But importantly, many of these proposed operations are still linear. And as one might imagine, one can only go so far when you are limited to only signal-independent processing. Moving away from purely linear operations, there have been some spatial audio effects based on directional audio coding, which is a method that operates in the time-frequency domain, with past spatial audio effects being based on the original first-order formulation. The idea is that for every time-frequency tile, we extract a directional arrival estimate and a diffuseness measure. These parameters are then used to try and reproduce the direct sound components as point sources, and this is accompanied by an isotropic diffuse stream, which is based on decorrelating many replicas of the omnidirectional signal and spatializing them all around the listener. The balance between these two streams is then dictated by the diffuseness parameter. So essentially, spatial audio effects based on Dirac work by simply manipulating these spatial parameters, changing the reproduction directions and the diffuseness value that's being used to balance between the two streams. A number of spatial audio effects can be realized. To briefly summarize previously proposed spatial audio effects that are based on ambisonics, they have generally either been based on linear operations, in which case they've been limited by the maximum spatial resolution that can be obtained with signal-independent processing, or the effects have been based on the original Dirac formulation, which aim to go beyond what one can do with only linear processing, but they are limited to first-order inputs, and they only sought to estimate the direction of a single dominant sound source at a time. However, the field of parametric spatial audio processing has evolved a little bit since the first formulation of Dirac was proposed. For example, the relatively new compass method supports arbitrary input order and can estimate the directions of multiple simultaneous sources. The synthesis is also based purely on spatial filtering in order to divide the sound field into directional source components and into directional ambient sound components. From there, it is perhaps quite intuitive to see how one might take these individual sound components and the accompanying spatial parameters and manipulate them for the purpose of realizing spatial audio effects. Therefore, our contribution with this paper was to explore the use of the compass parametric model to revisit some previously proposed effects, which were originally based on and limited by the first-order Dirac model. But then, owing to the more flexible compass model, we also explored some new spatial audio effects and spatial editing workflows. And to demonstrate that these spatial audio effects can actually be implemented as practical tools, we implemented many of them as VST audio plugins. So the first effect we revisited was listener translation around a single ambisonic receiver. This works by first projecting the direction of arrival estimates onto a 3D surface, which dictates the source distances. So the main limitation is that the source distances need to either be known or assumed. However, once you have the source distance information, the reproduction directions for a translated listener with respect to the receiver can be determined based on simple trigonometry, as shown by the figure on the left. And if we also incorporate the 1/r distance compensation law, this translation effect can be quite convincing. In the developed audio plugin showed on the right, the listener position and head orientation can either be manually defined, or this information can be obtained via a virtual or augmented reality headset. Another effect that works just by manipulating the reproduction directions is spatial focusing or warping. In this example, we let the user place markers onto an equirectangular representation of the sphere in order to dictate directions where they wish to focus the direct sounds. If direct sounds are within the angular range of the marker, then they are pulled towards the marker with a certain degree of gravity. It's maybe quite a simple effect, but it's nonetheless one that is quite useful in practice, as it doesn't affect any of the ambient components in the sound field. And it should be noted that in principle, one can extend this to pretty much any other directional transformation. So many more spatial audio effects can be realized in a similar manner. The next topic that we explored, although not quite a spatial audio effect, was the idea of an automatic microphone boom operator. Here we used a particle filtering based tracker to follow clusters of directional estimates over time. The directions of these tracked clusters are then used to dictate the steering directions of beamformers. These beamform signals are then outputted as separate channels by the plugin. So we are effectively automatically decomposing a sound scene into its broadband sound objects. In this present example, the input sound field is of two speakers that are moving, and their trajectories even cross over one another, but the tracker is still able to follow them correctly. And that is because the tracker also models the velocities of the targets. Building on from the previous audio plugin, we also explored the use of this tracker for spatial editing purposes. So in the top right, we have one plugin which outputs the source object signals, similar as with the previous plugin, except now the intention is that the user can now modify these source object signals however they choose. They can rebalance their levels, reorder them, or apply conventional single-channel effects to each sound source independently. We then have a second plugin which takes the user-modified source signals along with the ambient signals taken from the first plugin, which is passed internally, and it reconstructs the spatially edited sound scene. Other spatial audio effects described in the paper then include a direct-to-ambience balance control, which lets you, for example, give more prevalence to the direct components in the sound scene, which is akin to de-reverberation, or the ambient components can instead be exaggerated. It's also worth noting that since the ambient stream is still represented in the ambisonic format, traditional linear spatial audio effects, such as rotations and sound field warping or directional loudness controls, can be applied to only the ambient components in the sound scene if you wish. Also, since the analysis and synthesis stages are decoupled, we can, for instance, use the spatial parameters analyzed from one sound scene to manipulate and reproduce a second sound scene. So this is effectively a spatial sidechaining. And finally, going back to listener translation, if you consider that the compass analysis is generally the more computationally demanding part of the method, if you have multiple listeners, then you can use the same analysis stage, but each can have their own head orientation and translational data, or HRTFs, informed to the plugin. And this processing workflow can therefore represent a computationally efficient means of reproducing a personalized rendition of the same recording. And finally, although not explored in this present paper, but if you happen to have multiple ambisonic receivers, then listener translation can still be possible with the compass framework, in which case you don't need to know or assume the source distances. We can use the same particle filtering based tracker that we used earlier, but instead here we track the directional intersections in 3D Cartesian space, rather than tracking directional estimates as unit vectors. Otherwise, the rendering can be much the same. And we look forward to talking about this project more in the near future. So to conclude this present paper, we explored the use of the compass method to revisit and explore new spatial audio effects. And essentially, we try to demonstrate that once you have the compass model implemented, then developing these spatial audio effects becomes relatively straightforward, and is also quite an intuitive way of doing things. And actually, the main difficulty when developing these tools was in regard to the user interface design and not the DSP. Since the majority of these spatial audio effects were based on simply manipulating the spatial parameters prior to synthesizing the modified sound scene. And that brings me to the end of the talk. Thank you so much for listening. Please feel free to ask any questions, also via email if you prefer.